Hello, everybody. Thanks for coming. It's a great event. It was great last year, but not in terms of size, certainly. It has grown a lot. It's a really great to see how much interest and excitement the deep learning community creates. And I think that's largely because of how well it works now. And I'll start my talk with talking a little bit about standard classification, which is what deep learning has really pushed forward, but then also focus most of my talk on what I think the future holds, and that will be, I think, question answering and much more complex types of reasoning. So let me start by saying that if done right, as in with the right team or partner, standard image and text classification can be extremely accurate now. And I'm not going to spend too much time on the sales pitch, and a lot of our customers actually see this as a first mover advantage and don't want me to disclose all the details, but I can focus on two use cases where our customers were able to have a very quick time to market with enterprise-grade classifiers. The first example of this is food classification. You might think, and I certainly thought in the beginning, how interesting could food classification be, but there are a huge number of applications for this kind of application. Basically anything from appliances in your kitchen to health or foodie apps, to diabetic patients who want to keep track of their calories. There are a lot of different things you can do with food classification. And since we've seen that come up so many times, we actually started building the most comprehensive and accurate food classifier in the world. I don't think any other library out there has as many different kinds of food categories as this one. And I just show you here a couple of the items that are in this list, and we're still only at B. So it's a lot. Certainly there are a lot of things that I don't think I could even recognize. This one, for instance. Just to show you here a quick example, those are strawberries. It has different kinds of dishes in there too. So for instance, identifies this one as a pad thai dish. So food is interesting, but in some ways not as surprising that we're able to do well and actually have paying customers who are interested in that. What I'm even more excited about is actually in the medical domain. And here our partner VRAD, Virtual Radiologic, is really excited to share this. I can't disclose too many details. I don't want to take away their thunder in their press release that will come out soon. But basically, we're literally able to save lives with deep learning, which is not a statement that I thought I could make anytime soon when I started this company 3 years ago. So what is intracranial hemorrhage? It's basically brain bleeds, and it's one of the deadliest kinds of things you could find in a head CT scan when you come into the emergency room. It's really something that if you have it and it's bad and it grows, in 10, 15 minutes, you could die. And if it's diagnosed, you would want to have a hole drilled into your skull, put a catheter in, let the fluid and the blood out. So it's a pretty urgent kind of thing, and if an algorithm could identify that that is evident in a CT scan, you could very quickly put that on top of the queue of any attending physician and of the radiologist. And that's what we're doing, and it's now classifying thousands of CT scans every day, and from time to time has really urgent cases that it actually prioritizes and potentially saves those people's lives. So that's very exciting, and that is certainly one of the use cases that I think will only grow in the future. I think radiology will have a huge shift in the next decade where we can make them more efficient and maybe even provide that kind of technology in areas of the world that don't have as many amazing radiologists as the United States does. So that works right now. Basically, with deep learning, again, classification is to a large degree solved. Creates very happy paying customers. But not every problem is as simple as classification, and several require reasoning, and I think pretty much all natural language processing problems, and maybe even all AI problems, can be reduced or seen as a question answering problem over some input. To give you an idea what I mean by this, let me show you a couple of natural language processing tasks that have usually quite different subcommunities inside NLP that work on different problems. So the first one here, we have a problem that requires some logical reasoning. Mary walked to the bathroom, sent her into the garden, Daniel went back to the garden. Sandra took the milk there. Where's the milk? Now you need to find out something about the milk. For instance, Sandra took the milk there, but you still don't know where it is. Now you want to find out where Sandra is, and she went to the garden, so the answer is garden. So some simple logical reasoning like this is usually done with very different techniques to the next task, which is sentiment analysis. You say everybody's happy, and you ask, what's the sentiment? Or Jane has a baby in Dresden, and you ask, what are the named entities? It's just location, person, and so on. Have some lower level tasks like part-of-speech tagging that you can ask, or you can even ask, what is the translation into French? And the answer would be, the sentence in French. So this is just a small set of examples for NLP, and I'll show you later some for Vision too, that really show how general the framework of question answering is for different problems. So maybe a reasonable goal for the future would be to try to build one joint model for general question answering. And then maybe we would actually have a more significant chunk of AI solved in this path. So there are two major obstacles to this. The first one is that, at least in natural language processing, there's no single model architecture even with consistent state-of-the-art results across different tasks. If you try to do this question answering task I showed you with logical reasoning, you used to have this be the state-of-the-art, a paper from Facebook. For sentiment analysis, it used to be tree LSTMs. So LSTMs are usually used as a recurrent architecture, but in tree structures, syntactic tree structures by Stanford. I think Chris mentioned this yesterday, Chris Manning. And for part-of-speech tagging, you would have some bidirectional LSTM, conditional random field kinds of models to combine that. So up until we published the paper I'll talk about next, these different models were state-of-the-art in these three respective tasks. The second major obstacle is to have actual fully joined multitask learning. Whenever we do this kind of thing in the community, usually we restrict it to lower layers. For instance, in convolutional neural networks, we take the first couple of layers of the convolutional neural network that just find edges and things like that, and we replace the top classifier at the end. Or in natural language processing, we use word vectors and we share those, but we replace the rest of the architecture. It usually also only helps if the tasks are somewhat related, and in many cases hurts performance if the tasks aren't related. So for the next couple of slides, I will tackle the first obstacle. And I will use a new architecture that we developed in our research team at MetaMind called dynamic memory networks for this. It is essentially an architecture for arbitrary question answering tasks. So let me give you an overview, and then I'll talk about each of the different modules separately. One way to think of these modules is also to push deep learning away from here are some intertwined equations to, let's think about this in terms of software engineering a little bit too. You can have each of these modules communicate all directly via vectors and essentially train them all jointly with basically all backpropagation and the vectors both during forward and backward propagation be communicated between these modules. So the task here, to just illustrate this model, is the problem of asking, where's the football? That's the question, given these facts. And ideally, the model would give a correct answer, which would be hallway. And so the way this works is that essentially we have an input module that reads all the inputs that are relevant to the current task, the current question. It will compute in the question module a vector, Q, for the question. And then this question module will trigger a so-called attention mechanism that will pay attention to facts that seem relevant at the time to answer this question. For instance here, when I ask, where's the football, the question, the inputs that seem relevant are those that mention football, such as John put down the football. So here, this sentence is paid attention to, and then added to the main novelty in terms of the research of this work, which is the episodic memory module. Now, the episodic memory module essentially collects all the information that seem relevant at a time, and then stores it in a vector M. And at the end of each iteration over the inputs, the model knows, do I have enough information to answer this question, yes or no? And if the answer is no, it will actually go over the inputs again with the newfound information. So in the first iteration, for instance, I saw John put down the football, but that still doesn't really tell me where the football is. It just tells me now I need to figure out where John is. So it goes over the inputs again and now pays attention to any sentence that mentions John and picks the last sentence here where John went to the hallway. And then the final output of the episodic memory module is given to an answer module that will be basically just generating the answer. So let's go over the modules a little more in detail. To spill the beans a little bit, each of these modules is essentially a very complex recurrent neural network. So let's start with the input module. I'm not going to go into too many equations here, but this is the only slide with some equations. I probably think that if you have never seen any of these, I'm not going to be able to really explain it fully now. But what you can see is that these are essentially, for the most part, very standard neural network architectures. You have a standard linear layer inside and an element-wise nonlinearity. And you take as input at each time step a vector. Usually these are word vectors in our case for NLP. And you have the previous hidden state at the previous time step. And you compute the new time step by basically computing two types of gates, a reset gate and an update gate. And those are just standard single layer neural networks. There's no magic there. And then the main novelty here is that you have the reset gate, and the interesting idea of this gated recurrent unit is that the reset gate can essentially tell you, should I care about what I've known in the past? For example, if these R's here are all 0, I will ignore all the stuff I used to know before in my hidden memory state. So for instance, if John moved to the bedroom, it becomes completely irrelevant once I know that John is now in the hallway. So I can reset that memory and ignore it. And then Z is related in that it can also just copy previous time steps forward. So if the Z's here are all 1, I can just essentially set my new time step to the last time step, and I ignore what my input is right now. Intuitively, what that means is if John moved to the bedroom and the next sentence is Sandra went back to the kitchen, well, my question now, my attention, the facts that I'm paying attention to only care about John. So I can essentially ignore all the facts about Sandra as I go over the inputs. And that's what these gates allow us to do. So it's essentially an advanced recurrent neural network architecture. So if you're really interested in that and you thought that was the most interesting part of the talk, I give a lecture at Stanford, Deep Learning for Natural Language Processing, and I'll spend many, many hours just going into all those details. It's online right now, and I'll give it again next quarter. So basically, now that we know what a gated recurrent unit is, at least somewhat, a standard recurrent neural network, we can use that same architecture to compute the question vector. Again, we just have vectors of words as inputs. We compute them with a GRU to get the vector Q. Now, the interesting stuff happens in the episodic memory module, where we essentially have now these gates G that take as input the questions and the current time steps of the inputs. And the only equation that is not very pretty, and I promise also the last one of this talk, is this one. And you might think that that looks quite hacky, but really what it is a bunch of similarity functions. So you can have element-wise similarity, you can have simple distance functions, you can have bilinear products and things like that. And then you plug those into a standard neural network again, and that G function gives you essentially your gate. And that gate says, is for this question Q, is this sentence S actually relevant or not? And it also takes into consideration the memory that I have, so the previous facts that I've already looked over. And then again, if the summary, the end state of that gated recurrent unit is insufficient, which we can also train in training time, then I will go over the sequence again, but now my memories have changed because I use the facts that I've already collected from previous time steps. All right, so usually I try to stay away from anything neuroscience because I'm not a neuroscientist. I've collaborated with some. But here we did actually get inspired by neuroscience, largely because the episodic memory is the memory of autobiographical events, times, places. So I can ask you, remember that first kiss you had or something like that, and that brings back that time in your life where that event happened. So it's essentially a collection of the past personal experiences that we all have that occurred at a particular time and place. And it turns out the hippocampus, which is the seat of the episodic memory in humans as well, is active during transitive inference. And transitive inference was exactly the kind of task I just described to you, where we first need to know that the football is related to John, and then need to know what location John is in. Those kinds of inferences turn out to happen exactly in the episodic memory of humans, and that's why we named it the episodic memory module. And we've also run experiments and know that if you don't have multiple passes inside the episodic memory, you can't do transitive inference. The final module is the answer module. At this point, you'll have no surprises. It's also a gated recurrent unit, a recurrent neural network that essentially has a standard classifier output at each time step that outputs a word. Now, there are lots of different kinds of questions you can ask, and the Bobby task has several. So some have single supporting facts or multiple supporting facts. You can have yes-no questions, counting questions, how many people are in the scene or something like that. You can have lists and sets. It learns automatically negation, co-reference resolution, so you can say he went somewhere and it figures out who does he refer to. A lot of interesting subproblems, and this model is right now the most accurate model in the world and outperforms the memory networks from Facebook as well. So I have a little live demo that I put together. So here is an example of a story of a bunch of facts. And the question is, what color is Bernard? And so as we go over this, we can essentially see, and I'll give you a second to try to figure out the answer for yourself or figure out how to figure out the answer. What we see here is that the model essentially does it the way we would do it. The question is about Bernard. So it first pays attention to any sentence that mentions Bernard, which is just Bernard is a frog. It now knows it doesn't know enough, so that's good. It's a known unknown. Then it figures out, okay, maybe we should look for frog as well. The next important thing to pay attention to is that Lily is a frog. And then we still don't know enough, but now we know that Lily is yellow. And then it figures out, okay, now I know what the color is. And this kind of stuff used to require a lot of hand engineering for different rules. And you can hand engineer rules for simple examples like this, but what it shows us is if we can now have more complex examples, and we actually have the training data, for instance, customer support requests, we can now basically try to reason over the inputs and give better answers to customers. And the way it did it is purely by looking at vector representations of inputs and words. There's no discrete hand-tuning of features. Now, we can also have some other kinds of problems. We can ask, what is the sentiment? Sentiment analysis, pretty popular task. And here, we basically give it a pretty hard example. So despite the glowing reviews, this movie wasn't an especially engrossing experience. It's tricky because it has glowing reviews, which is very positive, and an especially engrossing experience. It's a very positive trigram too, but with the negation, it learns that it's negative. We can also ask, what are the named entities? The task I brought up in the very beginning, and we see here that it also very accurately identifies different locations and organizations and things like that, like the Kia Motor Corporation. We can also ask, what are the part-of-speech tags? And this is actually the most accurate part-of-speech tagger, which I don't think is as relevant for some sort of industrial applications, because these used to be sort of subtasks we needed, but now that we have these end-to-end architectures, I think we can solve the harder, higher-level semantic tasks right away. But it does give you a small amount of bragging rights, because this task is around 20 years old. This data set is 20 years old. You've had thousands of linguists and computational linguists work very hard on this data set, and the same model that gets state-of-the-art on question answering and outperforms Facebook, and the same model that gets state-of-the-art on sentiment analysis and outperforms Google and lots of other researchers working on that sentiment analysis data set, that same architecture also gets state-of-the-art on part-of-speech tagging. Because the model makes zero assumptions about language, we can also ask it about different languages. Again, it's just a matter of having question, answer, and input triplets to train the model, and then it will figure it out too. So here we have Chinese. I'm not going to fool myself by trying to read that out, but it's a pretty interesting sentence, and it also is a very accurate sentiment classifier for Chinese. It can also do machine translation, can ask it questions. In fact, just a couple of days ago, we now have one of the most accurate machine translation systems in the world. And I mentioned that it's more than just NLP. We can also ask questions about images. And so here, let me just go back really quick. The only difference that we have is we change the input module. Instead of having word vectors and sequences over words and sentences, we take mid-layer vector representations from images and give those as input to the episodic memory module. And the remaining modules are the same. And Kai Ming, who is one of our researchers at MetaMind, has now gotten this to be the most accurate model for visual question answering in the world. In fact, he outperforms anybody else on VQA. The VQA data set from Microsoft. And here are just a couple of examples. So for instance, we can ask what sport is shown, and the answer by the model is tennis. And I have a couple of other ones here. So is the girl an athlete, for instance? The answer is yes. There are a couple of other kinds of images you can use and ask different kinds of questions about it. It's really quite general purpose, and you can ask any kind of question about this. So is there a clock on the building? And the answer is, again, yes. And now imagine what I showed you in the beginning with food classification. Instead of just saying, here are a set of discrete classes. It's either pad thai or pad see ew or strawberries and things like that. Instead, having a model like this where you can say, all right, what's the food? But then, is it healthy? How many calories does it have? How long will it take to expire? Should I put it in the fridge or not? How should I make it? How should I create this dish? There's so many things that are related to questions. Like in some ways, questions are the most natural way we could possibly interact with future AI systems. So with that, I want to summarize. Essentially, if you have a concrete vision task right now where you want to identify anything in images, contact us. We're building, I think, the most accurate custom solutions, enterprise-grade, anything from food to complex things like radiology. And then for most, on the research side, most natural language processing tasks and multimodal tasks and vision tasks can be reduced to question answering. And the dynamic memory network is a very accurate model that solves a whole variety of different question answering tasks. Thank you.